All right, let's get started with today's lesson. And this is one of my favorite lessons because it kind of brings together a lot of the things that we've learned this year. So first of all, let's take a look at a couple of review questions so we can get ready for the RISE test. So we're asked to write this number, 357,000 in scientific notation. So remember, what we need to do is find our decimal and then move the decimal either left or right until we have created a number that is between 1 and 10. So in this case, we've moved the decimal 5 places to the left, and we now have the number 3.57, and we don't have to write all the zeros. And then we're going to multiply by a power of 10, and the power of 10 that we are going to use is 5 because we had to move it 5 places to the left, right? And that's why this is a positive exponent. Okay, the next one, we actually have to move the decimal to the right, 1, 2, and 3 places to the right to get a number that's between 1 and 10. So there's our number, 1.435. And we're going to multiply that by a power of 10. And because we had to move the decimal 3 places this way, or 3 places to the right, our exponent is going to be -3. -3, just like that. So that's how you do those scientific notations. Have a big number or have a really small number. Okay, now a certain solution has a hydrogen ion concentration of 9.14 times 10 to the -6 moles per liter. Write this number in standard notation. So what we're going to do now is we're going to kind of work in reverse order. We have to move the decimal 6 places back to the left in order to get this back to 0. So in order to do that, we're going to move it 6 places to the left, like that. And so what we're going to end up with is 0.1, 2, 3, 4, 5 zeros, and then our 9, 1, 4. So the decimal started here. We had to go back 1, 2, 3, 4, 5, 6 places to the left to get it back to where it's in standard notation. An African bush elephant can weigh up to 28,000 pounds. Write this number in scientific notation. All right, so the decimal starts after that last 0. And then we have to move it 1, 2, 3, 4 places to the left. So when we write our scientific notation number, we'll go 2.8 times 10 to the 4th power. All right, let's move on. So today we're going to be talking about what we call a line of best fit. Now we had a whole unit on what we call linear equations and how to make a line that has a positive or negative slope, the y-intercept, and different things like that. So today we're going to kind of use that line in connection with the idea of a scatter plot that we learned about yesterday or earlier today. So the line of best fit is basically a straight line that approximates the data that you see in a scatter plot. So you can see all these dots, they seem to be clustered together along a generalized linear pattern here. So to draw a line of best fit, we do something that looks like this. Well, we'll show you with this data right here. The line will come up through the data and try to hit as many points as possible, and trying to leave as many points above the line and below the line as well. So it might look like something like this. Now these straight lines that we're going to draw are approximations. So it's not going to be exact for everybody when we do these, but you can get them pretty darn close. And something that I think we should emphasize is that when you draw a line of best fit, you know it's going to come down and eventually hit the y-axis down here. You may want to pick a line and try to orient it where it's going to hit a number down here that you can recognize. This one happens to be headed straight for the 100 on the y-axis. And so that's going to be helpful for future applications. Okay, so there's a line of best fit on that one. Let's try another one. What would a line of best fit look like coming up through this cluster of data? And this one happens to represent sea level rise over the passage of time. And of course, the sea level was measured at a lot of different places. So in some places, it wasn't, the amount of rise that they mentioned wasn't as high as in other places, because there's so many things that come into effect, like the tide and everything else. So a line of best fit might look something like this. See how this line just kind of cuts the data in half, comes down through there, and has the same general slope. And then this line, when it comes down and hits the y-axis, like that, it's somewhere around 20 or negative 20. Well, negative, it's kind of hard to tell. Negative 18, something like that. Now, some of you might be saying, well, how can it be negative? Well, the reason why it can be negative is because because of the tides and everything, the tides go up and down, and so that varies a little bit. So, and then this is the amount of sea level rise, okay? All right, so how about something else? So here's a section of data on a scatter plot, and these represent or show the number of hours worked and the amount of money spent on an entertainment last week by each of 21 students. So the bottom scale is how many hours they actually worked that week, and the scale going upwards is how much money they spent, like going to movies or other types of entertainment. And so as you can see, the more hours that they worked, it looks like they actually were able to go to more entertainment as well. And that, we might ask, well, why is that possible? And we think about that. But we're going to draw a line up through here. So I'm going to grab a straight line. And when I draw my line, I'm going to try and approximate the data. So I'm going to just start out with right here at 5 and kind of come up through here about like that. So, sometimes they might look a little high, might look a little low. That doesn't look too bad. So let's try that. Let's call that our line of best fit. Now you notice how I'm not saying that is the only place you can put that line, but I'm just kind of approximating. And then I'm going to go ahead and extend it up here to the edge of the chart. Okay, pull it down a little bit. Okay, so there's my line of best fit. About the same number of points above, about the same number of points below. And for every one of you, when you look at that data, your line might be a little higher for some of you. Some might be a little lower for some of you. It's just kind of, the more you do these, the more you kind of get a feel for what's a good line of best fit. Okay. All right, so here's some data points. This is the theater revenue in millions of dollars, and then the revenue for rental in millions of dollars as well to rent a movie. So these data points are going to represent, how much people go to the movie and spend money versus how much they rent. And you may be tempted to think that the more people go to movies in the theater, the less they're going to rent movies. But it looks to me like as you go over increasing in movie revenue or theater revenue, it seems like the amount that is being made by renting them is also going up. Okay, so let's maybe look at the data. The data points on the scatter plot below show the theater revenue and the rental revenue are generated by 25 movies. Okay, that's a little more different. So it's important to understand the data. The data actually represents how much a particular movie made in the theater and also how much it made by people renting it. So that's a little bit different than kind of the spin I was going on. All right, so let's grab a line, bring it up through the data, about like that. I don't know, does that look a little high? That doesn't look too bad. That looks like a pretty good line that kind of approximates about the same number of points below as the same number of points above, and kind of a trend towards where the data may have started. Okay, so you're just kind of getting practice making a line of best fit. Now, if this was you making the line, if you made a line that looks like this, probably looks a little off. If your line goes like this, that looks a little off. And if your line looks something like this, that's probably a little off too. You kind of got to approximate the slope and, you know, the kind of the general direction of the line. Now, what you may notice is that over here on the left side on the y-axis, I'm trying to intersect the y-axis at a known point, if I can do it without making the graph not look accurate. And also, somewhere up along the line, I'm hoping to hit some other intersection where two other lines cross, because it will make things easier on me in the future. Okay, here's another line of or set of data that we want a line of best fit for. This data represents the amount of time spent watching television and the amount of time spent doing homework last week for each of 21 high school students. So I'm going to grab my line, and it looks like I'm going to start somewhere up around 28, 27, somewhere around there. I'll bring my line of best fit down, and if I hit about right there in the corner, that looks pretty close, but it might be a little higher too. I can't see. I'm going to go with this right about there. That looks like a pretty good line of best fit to me. And you know, you might make yours a little different. So like I say, the more you do this, the better you get at it. Okay, now what we're going to do is use a line of best fit to answer some questions, because lines of best fit are designed to help us predict or use the data that we've collected to kind of move into the future and predict what may happen. Okay, so the scatter plot here shows the time spent texting, X, and the time spent exercising, Y, by each of 24 students last week. So here's on the bottom scale, we got the time spent texting, and then down the side, we got the time exercising. So we drew a line of best fit that goes down through the data, and the line that we came up with is y equals negative 0.74x plus 8.54. And those are some decimal numbers, so they look a little bit intimidating, but you know, if we need to calculate something, we got a calculator, we can do it. So we're going to answer some questions now. What is the predicted time spent exercising for a student who doesn't spend any time texting? Okay, so if you don't spend any time texting, get our little marker here so we can kind of show that. So in no time texting, if you come up here, somewhere right around here is where that line is going to come up and hit at no time texting. So right now it looks to me like about 8.5 hours, 8.6 hours. So we'll go with 8.6 hours because it's just a little above the halfway point. What is the predicted time spent exercising for a student who spends 4 hours texting? So if you go to 4 hours texting and make a nice little straight line or dot line up to your line of best fit, and then you turn and go left this way and hit the y-axis, you're going to be right around 5.5 hours. Okay, and then the last one, for an increase of 1 hour in time spent texting, what is the predicted decrease in the time spent exercising? Well, so if we notice that for the 4 hours, we had 5.5 hours of exercising. So if we spend another hour texting, so if let's say we spend 5 hours texting, and I'll use the black, we come up and hit the line, and then, there's where we hit our graph, our line of best fit, and then we turn left and come over this way until we hit the y-axis. So that means that if we go another hour of texting, then we're going to exercise for a half hour less. So we subtract that 5 hours of exercising. So we end up with 0.5 hours. So for an increase of an hour of time spent texting, what is the predicted decrease in the amount of time exercising? 0.5 hours of decreasing exercise time. So over time, that could matter quite a bit, especially if you get into texting a lot and don't hardly do any exercising, right? Okay, so our assignment is on Alex. It's called Line of Best Fit, and you're going to be practicing making some lines of best fit, and then you're going to answer a few questions about lines of best fit. So good luck.